This is the second video in Chapter 8. Here we're going to cover the case where we're estimating the mean of the population, but we do not know the value of sigma, the population standard deviation. In the textbook, it's just referred to as the case where sigma is unknown. Now here's a little visual representation. We have the population, and what we want to do is to estimate what the value is for the mean of the population. We're assuming that we do not know what sigma is. So because we don't know what sigma is, we're going to have to use S, which is the sample standard deviation. The X bar is still the point estimate of mu, so we're going to have the X bar plus and minus the margin of error. But the margin of error in this case isn't going to be based on the Z distribution. It's going to be based on something called the student's T distribution. If we don't have an estimate for sigma, we can make use of the sample standard deviation to come up with an estimate. We're just going to call that the sigma unknown case, but it's based on what's called the student's T distribution, and there's kind of a somewhat interesting story about that. When you hear the word Guinness, what do you think of? Do you think of world records, or do you think of beer? The Guinness Brewery Company in Dublin, Ireland has been around for a long time, and there was a fellow that worked there by the name of William Gossett, and Gossett is the person that developed the T distribution. Evidently they had a lot of data sets where they knew that they had normal distributed data, and we're going to assume in this case that our populations are normally distributed when we use the T distribution. But Gossett developed a mechanism for using the sample value when they didn't know what the population value was. But Guinness did not want him to publish the results. They kind of had a policy that says we don't want our employees doing things like that. But he eventually talked them into doing it, but there was one proviso. He couldn't put his name on it. They didn't want other employees doing something similar to that. So when he turned in the paper, he signed it as a student of statistics. And ever since then, it's been referred to as student's T distribution. But it's my understanding that William Gossett is actually the person that developed it. And it turns out it's incredibly useful. Now the T is actually a whole family of distributions. You come up with different values based upon something called the degrees of freedom. For this particular T distribution that we're going to be using here, there are n minus 1 degrees of freedom. You take the sample size minus 1. Now as your sample size gets larger and larger and larger, the T distribution approaches the normal distribution, the Z distribution. Now this picture shows the normal being the curve up at the top, and then the one in the middle is a T distribution with 20 degrees of freedom, which would correspond to a sample size of 21. The one that's down at the bottom is a T distribution at 10 degrees of freedom, which would correspond to a sample of size 11. Now you can see that the smaller degrees of freedom, that the curve is spread out more. You're going to have more area that's in the tails. When you get closer and closer and closer to the normal distribution, it's because your degrees of freedom's increasing, which for this procedure turns out to be an increase in the sample size. But as your sample size gets bigger and bigger and bigger, as your degrees of freedom increase, the T distribution becomes more and more closely related to the standard normal distribution. The T at infinity degrees of freedom is the normal distribution. And sometimes people will use a T distribution table to get Z values if they've included an infinity row, because it's easier and ordinarily you can get more decimal places. The one that's in the textbook, I think it's accurate to 3 decimal places. So when you look in the column that has the 0.005, if you go down to infinity degrees of freedom, you get that 2.576. but you get that third decimal place. But here's kind of a cutaway of the t-distribution that's available in the textbook. And you can see in the 0.005 column, in the infinity row, you have 2.576 for the t-value, which will also be z because it's at infinity. But you can get that extra decimal place by looking at this t-table. Now, I've made available a t-distribution table that's a little bit better than the one that's in the textbook. It has a few extra columns in it, and it has several extra rows in it. It doesn't skip. It goes all the way from 1 all the way up to 100 in just increments of 1, and then it starts skipping. But it has more complete coverage than the one that's available in the textbook. It's also accurate to 4 decimal places. Now here again is the flowchart document. If you're trying to work out a problem, you would see that it involves an interval estimate of the mean. And when you get to the question, do you know sigma? The answer is going to be no. And then you get to the question about the normal population. Well, we're just going to assume the normal population and just go ahead and use the t. If you don't have normal data, if you have the big sample size, since the means become closer and closer to normal as the sample size increases, you can still get by with the t-distribution even if you don't have underlying normal data. But the formula is x bar plus or minus, there's a t-value, and you have n minus 1 degrees of freedom. Now the formula in the textbook, that subscript's not n minus 1, it's alpha divided by 2. You need that probability that's in the upper tail to use the t-table. But we don't know what sigma is, so we just plug in s and divide it by the square root of n. But it's the same general form as the previous confidence interval estimate. You have the point estimate, in this case it's x bar because we're estimating the population mean, plus or minus the margin of error. But the margin of error, because we don't know sigma, is based on a t calculation. We don't know sigma, so we use s, but the form is the same. Now this is the example problem that we're going to use to illustrate the procedure. It has to do with apartment rents. They're trying to come up with an estimate of the average price to rent an apartment, a one-bedroom apartment that's within a half a mile of campus. Now they're going to assume that the population is normally distributed, but in this problem we don't know what the value of sigma is. We have a value given to us approximately for the sample standard deviation. They're saying that's about $55. And the mean of the sample, they took a sample of 16. The mean of that sample was 750. So we have our point estimate value. And what we have to do is to take the s, divide it by the square root of n, and then multiply it times the t value that we get from the table to come up with that margin of error. And we can just add and subtract it to the sample mean to get our interval estimate. Now the t-table works on the probability that's in the upper tail. So if you go to the column that has 0.025 in it, the reason that we're using 0.025 is we want a 95% interval estimate. So that means that the alpha value would be 5%. It's just the complement. But you'd have half of that in the lower tail and half of it in the upper tail. So the probability that's in the upper tail is what you use to identify the column in the t-table. The row is identified by the degrees of freedom. Commonly you'll see DF used as an abbreviation for degrees of freedom. But we had a sample size of 16, so there are 15 degrees of freedom. So you intersect those two things. We're in the 0.025 column and we're in the 15 row. And the number here to 3 decimal places is 2.131. So that's the value that we're going to multiply times s divided by the square root of n to get the margin of error. So we take 55, the value that was given to us for the sample standard deviation, divided by the square root of the sample size, square root of 16, and then multiply it times the number from the t-table, the 2.131, and that gives us the margin of error. And then we just add and subtract that to the mean value, which was 750. So the upper bound, when we add it, we get $779.30, and the lower bound, when we subtract the $29.30 from the $750, we get $720.70. So we're 95% certain that the mean rent, the average rent, for those one-bedroom apartments that were within 1/2 mile of campus, it's somewhere between $720.70 and $779.30. So if somebody has a budget and they say, well, I don't want to pay more than $800, well, there's a pretty good chance they're going to be able to find one. The average price is unlikely to be above $779.30. Now, Excel has a facility in it that will calculate that margin of error. It's in a tool that's called Descriptive Statistics. If you go to the Data tab up at the top of Excel, you may have the analysis group in there. If you don't, there's a way that you can add it, but you have to go through about 4 or 5 steps to add it in there. But once you get it in there, you can click on this Data Analysis Tool Pack. And one of the tools that's in there is Descriptive Statistics. And then all you have to do is just click on Descriptive Statistics. If you just click on it, then you click on the OK button to get it, or you can just double click on it. And then the dialog box is going to open up. This slide shows the dialog box. The input range, all you have to do is select the data. Here in A1, they put the rents, the word rents, it's a label. So they check the labels in the first row. And then A2, A3, all the way down to A16, that contains A17, excuse me. That contains the data values themselves, but there's 16 in the sample. A1 has a label, and then A2 through A17 contain the 16 data values, and they're set up in column. We're going to take the output and put it starting in cell C1, and we check the box for the summary statistics, and we check the box for the confidence level for the mean, and we want the 95% interval estimate. So one of the things that Excel will do for you is it'll figure out, based on the t-distribution, it'll figure out what that margin of error is, and then you can add it and subtract it to the value of the sample mean, and you can get the interval estimate. This slide shows the numerical results for the descriptive statistics. It took and put the label in C1 and D1. The mean was calculated in row 3. It's in cell D3. And down at the bottom is the margin of error. It's labeled as the confidence level. In this case, we chose the 95%. And Excel has calculated it to be 29.31486. Now you'll notice that that's a little bit different than the 29.3 that we did with the value from the table. The value from the table was rounded off to 3 decimal places. Excel's probably going to be using in the neighborhood of 15 decimal places for a t-value. So you're going to get a little bit of a difference, but it's just due to round-off error. But if you take the 29.31 and add it to the 750 and subtract it from the 750, that's going to give you your confidence interval estimate. Now, addressing the sample size issue, if you have normal data, the t-distribution is going to work just fine. But if you don't know whether or not the data is normal, as long as you take 30 or more, this formula should work out okay to estimate the population mean. The sampling distribution of the mean is approximately normal when you get 30 or more. Now, if you have a really highly skewed set of data, then you probably need to take a bigger sample size to kind of address that issue. 50 or more is usually considered to be adequate. Now this simplified version of the flowchart should be okay to address the homework problems. If what you're trying to do is to estimate the population mean, just ask whether or not you know the value of sigma. If you know the value of sigma, then use the z form. X bar plus and minus the z value times sigma over the square root of n. Now if you don't know what sigma is, don't worry about the normality, don't worry about the sample size. Just use the t-distribution. Take x bar plus or minus the t value times s over the square root of n. Now this concludes the video over estimating the mean where you don't know sigma. I'm going to use a different video to cover the case where you're trying to estimate that population proportion. The mean is when you have quantitative data. That's typically what people analyze. But when you have qualitative data, in a lot of cases, people make use of the proportion.